Good day, good day, good day, and welcome to Africa Teen Geek. Yes, this is our STEM digital school. This is our online school. If you have just joined us in here, this is the grade 12 physical sciences classroom. This is the grade 12 physical sciences classroom. This is the 1st of July, and we are hitting it off with our term 3. I hope that you guys had a good rest and you've been studying hard and you've been working hard throughout the holidays since the last time you had class here on our digital online school. Okay, so today we're going to be doing a topic. We're starting the term 3 work. I'll explain to you guys why we're starting with what we're starting with right now. We are going to be doing the chapter on work, energy, and power. Yes, I think it's work, energy, and power. And basically, what we're going to do today, we're going to start with the first section. We're going to be doing a unit a day just to make sure that you guys understand everything. We don't want anybody to be left behind on anything. So today we're going to be doing the topic on work, and that's what we're going to be working with. So before we get started, I just want to remind you guys or let you guys know that I'm working mainly from the Siavula or the Study Masters textbook. So if you have one of those textbook, that's a bonus. But Oxford Successful Textbook is also a great textbook, and unfortunately you cannot get it anymore on the Snaplified application. It's been removed, but you can't get any other textbook there. So if you guys are looking for textbooks and you're struggling to get the correct textbooks, just go to Snaplified, get yourself registered. They're giving out textbooks absolutely free for the whole year because of the COVID-19 problems that happened this year. So this is an advantage for you guys to get as much books as you can, because as grade 12 learners, we are entering you are entering a big stage whereby it's a do or die, and we want to make sure that everybody here gets themselves some good A's. And please, guys, please use the do not use the video. Ne? We do not show videos. Just use the voice recordings. Okay. 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 So can you guys please just remove the voices, stop the videos? Yes. So that's what we're going to be doing here in this classroom. You guys can chat. You can ask any question on our chats as I go along. We do not show videos because, discretion and stuff like that. But there's my picture. If you want to see how I look like, that is me over there. And my name is Nonkululeko Matondo, and I am your teacher for grade 12 physical sciences. Okay. Uh, So be sure, guys, to download Snaplified if you guys get a chance. Okay. Okay. So assignments that have been done, they are not so much because everything is still the same. You still need to learn everything that you're going to have to learn. But what we know now is that work, energy, and power has been moved to term 3 because we did not have a term 2 thanks to our COVID-19. And our Doppler effect is also going to be part of the term 3 work that we're going to be doing this term. And from term 4, we're going to be doing electrochemical reactions and fertilizers. So everything is still the same. They've just changed. Term 2 becomes term 3 work, and the number of hours. So they have been reduced, but with us, we are going to continue the way we continue because our aim here is for everybody to pass and most importantly to understand what they are doing. Okay, so the trial and final exam of each will consist of 2 papers. So this one you already know, you're going to have paper 1 and paper 2, and that's how it's going to happen. Okay, so another thing that I wanted you guys to check quickly and mark is that your matter and material will not be weighing any mark anymore. Okay, it used to be 15 marks, but it no longer weighs anything. So electricity and magnetism, it's going to be 40%. Mechanics is going to be 48.7, and what we're doing right now is also part of mechanics. So we are on the right track. And wave, sound, and light is going to be 11.3%, which is didn't change. So just make sure that you got your mark weighing scales correct. Okay, and then for chemistry, this is what's going to happen. Chemical systems have been removed. Oh, thank you, COVID. So it used to be 18 marks. So now it's not going to be weighing anything. It's just going to be matter and material, 40 marks, and chemical change, 60%. Okay, 40% and 60%. So make sure that you scratch out all the things that you will no longer be needing for your end of the year papers. Okay, and good luck, guys. So today, what we're gonna be doing today, basically our guys, please don't go on the videos. Okay, thank you. Oh, okay. Ooh, I don't know what did I just do now, but I don't know what is happening. I've just gotten too far. Okay, sorry about that. So our content for today, we're going to define work done on an object by force. We're going to understand that work is a scalar. We're going to have calculations done on the network done on an object. We're going to understand the difference of positive, negative, and no work done. And then we're going to also learn how to draw force diagrams to determine the net work done on an object. Okay. So those are the things that we are going to be working with today. So introduction. So this is mechanics continued. Remember, we already started with mechanics earlier in the first term. So now we are continuing with that. Okay. So mechanics is got many definitions. Every grade that you've been through, they've given you a new set of definitions, but it keeps going on, and it's going to keep going on even in your university level. So each and every day, work is performed by all of us. Work is the ability to do something physically. I mean, to wake up, to sleep, to play, everything. All of that, it's work being done. As long as there's some physical action that you have to put into it, it's work. But work, however, has a specific meaning when we get to physics. Okay? In physics, work is the ability to transfer energy from an object to another, or changing energy from one form to another. So thereby, work is done. Okay? Guys, I'm just reminding you that we are not doing voice questioning and stuff. If you have any question, you can just send me a chat, or if there's something that you want me to clarify as I'm reading along, you can just send me a chat and tell me, and I'll go back and explain. Okay. So work in physics, work is the ability to transfer energy from one object to another, or changing energy from one form to another. You guys get that? Okay. So work is therefore the product of displacement and component of applied force. Okay. So what that means is that it's over here, there's going to be a displacement, right? But over here, we've got the force, right? And this force has a component. It's got two components, one going that way and one going up. Okay. So basically, the force that we're going to deal with is this one that is parallel to the displacement, and we're going to be ignoring the perpendicular one for now. So you understand. So this is your distance, this is your force, and this is your force, this is your distance, and this is your perpendicular force that's going to be moving this ways. Okay. So work is therefore the product of displacement and component of applied force, which is parallel to the movement of the object. Hence, I told you guys that as much as this is the force here, the component, we're going to have a parallel one and we're going to have a perpendicular one. So this parallel one is the one that we're going to be using to calculate our work done. Okay. So in this unit, we will soon understand that work and energy is closely related to Newton's laws of motion. So we do have a couple of Newton law of motion, but we're going to deal with them as we go through this chapter. Okay. So energy of an object is the capacity to do work. Okay. Energy of an object is the capacity to do work. And doing work is the ability to transfer energy from one form to another using a force. Okay. So I think throughout this chapter, we'll always, every now and then, the definitions are going to keep coming up. And you guys, that's going to be a form for you guys to start understanding each and every definition that you need to know. What is work? What is energy? What is physics? You know, all those things. What is displacement? What is applied force? So all of these things are things that you guys are going to have to know, because they can be asked in any form of question or even a multiple choice. Okay. Let's move on to the next. Okay. So work is what we're dealing with today. This is the first unit out of this chapter that we're doing here. Okay, what is work? Okay, on the Siyavula textbook, I think it is chapter 4, and on your study and master, it's chapter 3. So just be clear where you get them. This is the work, energy, and power part, and we're starting with work. Okay, so work, when a force acts in or against the direction of motion of an object, work is done on the object. Okay, so it can either be, for example, when we go to that boy that's pushing um, a box. Okay, in this case they're working um, in the direction of motion of the object because they're pushing it forward. They're not working against it. But it can also happen that the force is acting against the direction of motion of the object. Do you guys understand that? So that's what it means by when a force acts in or against the direction of motion of an object. In this case, they work in the same direction because the boy is pushing the box to the direction in which he is moving towards as well. Okay, so work is done on the object. Okay, so what do we know about work done? Work done is equals to F times triangle X times cos theta. Okay. So what are these? What is this? Let's break this down to understand how did they get to this formula. Okay. So this is obviously the work done in joules. And the F is the force acting on the object. And this will be what you're given in Newton. For example, they give you 30 Newton, 20 Newton, etc. That is a force that's acting on the object. And be clear that when you see that, when they give you a drawing like that, the arrows are pointing in the proper direction. Okay. So the triangle X, this is the displacement over which the force acts in meters. Okay. So this is the distance, this is X, this is where the boy was standing, and this is the force, and this is the distance. Okay. Or displacement. You can say the displacement over which the force acts in meters. Okay. And then the angle is the angle between force and displacement. So here we've got our displacement where the boy's shoes are displaced, where he's standing, and this is the hands, and this place here is the box. Okay, so this is the angle between the two. Okay, where the force is taking place and where the application is made. Do you guys understand? I hope that you do. So there's a special note that has been placed here. It says, note that the F cos theta is the component magnitude of F. Okay. So if you are given F in this case, I don't know how I can put it. There will be a component. Each and every force has a component. It's got a perpendicular and a parallel to the displacement. Yes. The component, there's one that is parallel, and there's the one that is perpendicular to the displacement. So those are the components of this force. Okay. So you'll have one cos and one sine, but in this case we only focus on the parallel component. Okay. So if the angle is is greater than 90 degrees, so 90 degrees would be right here, right? So if the angle is any less than 90 degrees, so which means it will be this side. All of these ones is what they mean when they say the angle is greater than 90 degrees. Then the component is parallel to the direction of displacement, but will point on the opposite direction, and force is opposing the motion. Okay. Oh, no, this one here, 90 degrees is greater than the angle. Yeah. So this one is 90 degrees, but it's less, the angle is less than 90. Okay. Let's move on. So basically, now you guys understand where the F cos theta comes from. The F cos theta is the component if the theta is equals to 90 degrees. So which means now we've got a straight perpendicular reaction. The magnitude of the component will be this component. Okay, y is equals to 0. So in that case, there will be no component. So which means that no work will be done. Okay, and then we move on. So now it's when the angle is greater than 90. The one before was the angle is less than 90, but now the angle is greater than 90 degrees, which is what you see here. The magnitude of the component along the parallel line of the displacement will be in the opposite direction, and the component will be a negative work done. Okay, so we see what's happening here, guys. The first one is when the angle is less than 90 degrees. It'll give you a positive work done. When the angle is equals to 90 degrees, the the F cos theta, the component will be equals to 0. So which means no work will be done on this component. Okay. And then the third one is when the angle is actually greater than 90 degrees. So along the parallel line of the displacement will be in opposite direction, and the component will be a negative work done. I hope that you guys understand the difference between the three components and the conditions that you guys might get. Okay, then moving on. Okay, so this is just a small example that I wanted us to see, because we're talking about forces acting on an object, etc. In the picture below, no work is done. So in all of these ones, no work is done. Why is that? The force and the magnitude is acting in the same direction. Okay. So which means this person is not standing, this person is moving, and the object is also moving. So no work takes place. Okay. The angle in each case is equals to 0. The work done can either be positive or negative. The sign tells us the direction of energy transfer. So energy is a scalar, meaning that the sign tells us whether energy increases or decreases. Okay. So if it's negative, it's probably decreasing. If it's positive, then it's increasing. That is what that basically means. Okay. I hope that everybody is understanding slowly the theorem of work done. Okay. So we're gonna go to a work example. Okay. So, but I'll go to the textbook now. I just want to read the question. This is page 225 on the Siavula textbook for worked examples. Okay. So a car is traveling along a straight horizontal road. A force of 500 Newton is applied to the car in the direction that it is traveling, speeding it up. Okay. While it is speeding up, it covers a distance of 20 meters. Calculate the work done on the car. Okay, let's go to that example. Okay, here we are. I just want to share the screen of this. Guys, I hope that things are slowly coming together in your mind, getting to understand. Okay, here it is. Okay, calculating work done on a car when speeding up. Okay, so now say a car is traveling along a straight horizontal road. A force of 500 Newton is applied to the car in the direction that is traveling, speeding it up. Okay, so that would probably mean like it's pressing the accelerate, right? While it is speeding up, it covers a distance of 20 meters. Calculate the work done. Okay, so what do you do when you get a problem like this? The first step is you need to analyze the question to determine what information you are provided with. So number one, here we've got the force, which is 500 Newton, and we've got the change in x, which is 20 meters. Okay, so now we can calculate the work done. Okay, the applied force and the distance are moving in the same direction. Remember what we spoke about earlier on is that when the applied force and the distance are moving in the same direction, therefore the angle between the force and displacement is 0. Okay, so once you see this, the 50 however is applied to the car in the direction that it's traveling. While it's speeding up, it covers this distance. So they said they both moving on the same direction. So that's why our theta is equal to 0 degrees. Okay. So these quantities are all in SI units, so no unit conversions are required. Okay. So what that means, it means that sometimes you get that they can give you this in kilometers. You will have to convert it to meters as the standard SI unit. Or if they give you this in kilonewtons, you'll also have to convert it to newtons in order for you to have the correct answers. Okay? So, step 2, now we analyze the question to determine what is being asked. Okay, we are asked to find the work done. We know that by definition, the work done is work is equals to force times distance cos theta. Okay, but in this case, we know that cos theta is equals to 1, and we start substituting everything. So which means in this case, basically we had force times distance. Usually when they're in the same direction, it's equals to force times distance, and because the cos will be 0, and that will give you a 1, and this will be your answer. Okay, so remember that the answer must be positive as the applied force are in the same direction. But if they had mentioned that the force is acting on the opposite direction of the moving car, then we would obviously have a minus force. It would be minus 500, you see, and this will give us a minus 10,000 joules. Okay, do you guys understand? I hope that you guys are all in line with these examples. I personally like these examples because they well widely explained. So that's why I preferred to do these examples from this book. Okay. So now they come back and say the same car now slows down when a force of 300 Newton, which is what we just spoke about, is applied opposite to the direction of motion while it is traveling, while it travels 25 meters forward. Calculate work done on the car. So once again, we do our first step. We analyze the question to determine what information is provided. Okay, so the magnitude of the force now is 300. We have it. The distance is the change in distance is 25 meters. The applied force and distance moved are in opposite direction. So which means that the angle in our case, we can have it as 180 degrees. Okay. So 180 degrees um, expresses the fact that it's 180 degrees out of phase. So it's opposite. It's acting oppositely. Okay. So these quantities are all correct units. So there is no conversion that is required. You know? So now is for us to go back and plot our given into the equation. Okay. So that will give us, so you see that even if you don't write minus here, as long as you have 180 here, it will give you a negative answer because 180 degrees cos 180 degrees is equals to minus 1. Okay, so whenever you hear opposite, you know that applied force and the distance are in opposite directions. The energy is being lost by the car. This may be energy lost as heat to the environment or etc. But energy conservation still holds. The energy has just been transferred to a larger system that contains the car. So in this case, we will have a negative answer because it's got a force that's acting directly opposite from the car. Okay, are you guys still good? Are you guys following? I hope that all is happening. So what happens when applied force and the motion are not parallel? By using the formula F times distance cos theta, we are actually calculating the component of the applied force in the direction of motion. Note that component of the force perpendicular to the direction of motion does no work. Okay, so that's the one going up. So we're moving on, guys. I want us to do this example so that it'll be easier for us to be able to do our homework, which is also related to the work that we're doing now. Okay, so calculating work done in a box, on a box pulled at an angle. So here's the angle. So here we can even write a straight line here and write an angle just here. Okay, so calculate the work done on a box if it is pulled 5 meters along the ground by applying a force of 20 Newton at an angle of 60 degrees to the horizontal. Okay, yeah, so they both move in the same direction again, eh? So we already know that it's positive. So what do we have? We have, if the box is pulled 5 meters along the ground by applying 5 Newton, we've got the distance, which is 5 meters. We've got the force, which is 20 Newton. And we've got the angle of the force, which is 60 degrees horizontal. So now we've got all our given. There's nothing to convert because they are all in our standard units. Okay, I think I might have jumped too fast. So you can just go straight to plotting the equation on the, we can go straight to plotting the equation. What is given? We've got 300, we've got 25. Oh, no, what's this? I think, gosh, I'm sorry, guys, just, working with a book, with PDF, it always gives you some funny stuff. Yes, here we are. Okay, so this is what we're given, like I've already mentioned. And from there, these quantities are incorrect. So yes, I already mentioned that. So now we can just plot it there. So note that the answer is positive as the component of the force parallel to the direction of motion is in the same direction. How do we know that they're in the same direction in this case? Because they said pulling. The minute you hear pulling, you know that it's in the same direction, because when you pull something, you're going in the same direction as the object that you are pulling. But once they say pushing, then you know that that one is an opposite force. Okay, let me just see if there's another example that we can get from. I just want to see if there's another example we can get from our Snaplify textbook. Okay, so this is our study and master textbook. There's also an example that I want us to check through. Okay, so it says here, figure 1 and figure 2 shows a 2-kilogram block. Determine the total work done when the block is pulled horizontally by 2 Newton over a distance of 10 meters on a frictionless surface. Number 2, when it's carried a distance of 10 meters at a constant velocity by a person. Okay, so how are we going to work this out? Let me see if we don't, where is our figure? Example 2, I'm just looking for our figure 1 and figure 2. Okay, so the first thing that we're going to do, finding the solution. The block moves horizontally, and the only okay, no, we don't have a figure here. Okay, what happens here when the block moves horizontally and the only horizontal force is applied on the force is 2 Newton? Okay, so this one is being pulled, so which means it's a positive force. So this force is the net force. This force is in the same direction as the displacement, so the angle is equals to 0. Okay, they're both moving in the same direction because it's being pulled. Okay, and it's a frictionless surface. So what do we have? We do not have friction. So what we're going to have in this case, it's straight the force times distance times the cos theta. But in this case, it's not important because we already know it's 0 because they're in the same direction. So it might as well have been force times distance. But it's always good that you write everything into its completion in order for you to get the correct answer, and to sometimes see, when you make an error, where you can get to fix your work. Okay, so the force applied on the block is vertically upwards. So what they say here, determine the work done on the block when it's carried a distance of 10 meters at a constant velocity by the person. So what does it mean? The force applied on the block is vertical upwards, okay, because it's being carried against the gravitational force. So both the applied force and the gravitational force are perpendicular to the displacement. So neither force does work on the block. So the net work on this block is 0 joules. Okay. Problem is this one, the constant velocity. So the force upwards. It's acting against the gravitational force. Both applied force and gravitational force are perpendicular to the displacement. Why? Because the force is moving upwards, so it would also be perpendicular to the displacement. So neither force does work on the block. Okay, guys, I hope this is. So let's do the last example, but we're running out of time, because I still want us to go through the homework that we're gonna do for tomorrow, that we're gonna do before class. Okay, so I hope these examples have sort of like made understanding much more easier, on how these work. So what we know from these examples is that and when a force and the displacement is moving in the same direction, the force is positive. But as well, when a force is being pulled, when an object is being pulled, it's also moving on the same direction. So which means that you have a positive work done. And for the opposite one, where a force is moving in an opposite direction, or it's being pushed, you know, then you have a negative work done. And remember that it's either 0 degrees, or if the angles are not given, it's either we have 0 degrees or we have 180 degrees for a negative force, if you don't want to write minus on your force being done. So either way, there's many ways to kill the cat. You just need to know how. Okay, make sure that you apply your equations properly. Okay, so please guys, if you guys have snapshots, please take a picture. This is our homework for tomorrow. Okay, for those of you that do not have this textbook, this is our homework for tomorrow. So exercise 5.1 homework is work. It says a 10 Newton force is applied to push a block across a frictionless surface for a displacement of 5 meters to the right. The block has a weight Fg of 20 Newton. Determine the work done by the following forces: the normal force, the weight Fg, and the applied force. Okay, so because this is our homework and I want you guys to do homework that you actually understand what is going on, I just wrote the answer to this one so that you can be able to do the rest. You can be able to do number 2, number 3, and number 4, which is what we're going to do tomorrow morning. I'm going to check your homework. Okay, so this is what we have on the block, what is given. So normal force acts perpendicular and therefore does no work. So whenever a force acts perpendicular to the displacement, then no work is done. Okay, so you can see here, this one, it's perpendicular to the displacement, so no work is done. And this one as well, this one, the weight, the normal force is this one, it's perpendicular, no work is done, so it's 0. So this one is also perpendicular, so it will also be 0 because it's perpendicular to the displacement. Okay, so but we have this one, this force applied. This one is parallel to the displacement, so in which case we will have a calculation there, we'll have a work done. Okay, so the weight acts perpendicular to the direction of motion and does no work. But with the applied force applied, we do have a work done. Here it's going to be F times triangle X cos phi. Okay, so but in this case, this one, it's not at an angle, so the cos phi is 0. The angle is going to be 0, and it will give you a 1. So you might as well just say F times triangle X, and that will be 10 times 5, and that will give you 50 joules. Okay, so the normal force is 0 joules, the weight is 0 joules, but the applied force, that is 50 J. So I hope that this one problem will make it easier for you guys to do all these other problems. If you just remember what we stated, which is the fact that perpendicular, if a force is perpendicular to the displacement, then no work is done. They have to be in phase. So basically, they have to be in parallel for them to be calculated. Okay, guys, are we good to go? Are we good in understanding what is happening with the forces? If you don't, guys, you guys can send me a chat with the little time that we still have. I hope that you guys understand the work and what it means, what work, how the forces work, because this is the foundation of this entire chapter, because we're just going to be working with weights, forces, and work done throughout this chapter. So if you don't understand what is happening now, you're going to have a problem in the future. So if you do have a problem, or if you find a problem while you're doing other problems, remember you can find me. Oh no, this is not my email address. My email address, it's